Hello, everyone. Good evening for those that are in Europe. Good afternoon for the audience in North and South America. Please let us know where are you from on chat. We saw people from Argentina, from United States, from Poland. We are always eager to see where we have the people interested in our talks. My name is Marcin Kosiński. I'm the founder of YR Foundation. Our aim is to support our community. And in current circumstances, we are heavily invested in webinars. We do them every Thursday, 6 p.m. UTC. This is the 12th webinar that we have. Next week, we are pausing because there's European users meeting happening remotely. Today, we have an excellent guest. I have a pleasure to introduce Dr. Erin Hodgess, who will talk about high-performance computing. And this is the 12th webinar that we have. Next week, Dr. Erin is a course instructor at Western Governors University. She teaches mathematics and statistics courses. And prior to this, she taught at the University of Houston downtown. Her research interests include time series geostatistics and statistical computing. This sounds like a mixture of a lot of interesting areas, and happy to see what we can do in those areas with the help of high-performance computing. So, Erin, the floor is yours, and let's have the presentation and let's have the questions at the end. And people, if you have any questions, post them on the chat and we will ask them at the end.
All right, so I'm going to go ahead and share the screen. Let me just grab this. Is everybody able to see all right with the YR?
I can't see it.
Okay, so I did the share screen. Just a second, please. Okay, I'm going to stop the video and I'm going to share the screen. Aha, that's why, because it would take common sense. Okay, so let's grab this. All right, now let's give it a shot. Okay. So today we're going to talk about using R with high performance tools on a Windows laptop.
Mm-hmm.
And
yeah,
so I'm going to present a brief overview. So we're going to have an introduction. We're going to talk about the package. It's MPI Fort, which is really for ordinary Kriging for spatial-temporal data. So we'll get some theoretical background for the geostat part, the empirical background, and then look at a couple of studies that we did. So the Irish wind data study is the most extensive and it has the most interesting results. Something that I did for fun was Cuba temperature data study. It's a small study, but you can see the outcomes. Then we'll actually discuss the how-to, okay? So we're going to talk about setting up the computer. We're going to look at OpenACC and the message passing interface, that is MPI. In particular, we'll make a brief reference to CUDA Fortran, and then we'll present a brief conclusion. All right. So several years ago, I had a wonderful opportunity. I was working on supercomputers for geostatistics research. So that was just on spatial data. And I was able to work with Stampede. It was actually Stampede 1 at that time from the Texas Advanced Computing Center, along with Bridges from the Pittsburgh Supercomputing Center. So as I mentioned, I worked strictly with spatial data and I was able to get some very nice speed up. But I was thinking about it, what if you don't have access to supercomputers? If you have a multi-core laptop, would that help? Particularly if you had one with the NVIDIA graphics card. There's a lot of software for that. So as promised, we're going to talk about ordinary Kriging on the spatial-temporal data sets. So essentially, you're going to take your spatial data and add a new dimension to it. So not only are you looking at longitude and latitude, but now you're looking at time. So is there an existing R process? Absolutely. Unfortunately, it's a little bit slow and it doesn't allow for large data sets. So I put together this package, this MPI Fort with the high performance tools on Windows. And you'll see in a little bit, we have our new process, and we're going to run comparisons on a MacBook Air and a Windows laptop that does not have the tools in effect. And we actually ended up with very good results. So here's our theory. We have our spatial temporal vector, Z, and we have Z with our spatial and temporal indices on each of them. We make a couple of good assumptions. We have our first order stationarity, which is the expected value of Z is just equal to some constant U. We also have second order stationarity. So when we're looking at our covariance for our spatial temporal model, we have the same sort of thing that you will run into in time series. That is, if you have your shift in space by H, that's the same as going from 0 to H. If you have your shift in time of U, then that's the same as going from 0 to U. So that's a nice carryover. So in both spatial and spatio-temporal processes, we have something called a semivariogram, and we're going to use that to select an appropriate model, and we'll see that in a little bit. So the semivariogram is constructed by using point pairs. So we have n times n minus 1 over 2 point pairs. So that can get very demanding very quickly. So one of the things that is done is constructing bins, and we set up what's called a range for the distance and direction. So again, if you're familiar with using exploratory data analysis, when you put together your histograms or your robust histograms in particular, you're going to be looking at bins there. It's the same basic kind of concept. So we're going to use the semivariogram to help us build our covariance matrix. And the covariance matrix is going to be key throughout this. So here's just a quick picture. Again, we're looking at some theory. We have our nugget. That's the variability that isn't explained by the spatial structure. We have the sill, which gives you your maximum semivariance. And the range is actually your horizontal distance between the 0 and the maximum value of the sill. Now, one other thing we're going to talk about is called the partial sill, and that is simply the difference between the sill and the nugget. So for instance, in this particular case, our partial sill would be 1 minus the 0.2, so that would give us 0.8. So it's pretty straightforward. All right. We're going to use something called authorized models, and we're going to fit our spatial, temporal, and joint aspects of our data set. So we use an automatic process which uses the minimum mean square error. And there are actually 15 authorized models. I know you're going to be disappointed. We're only going to use 3 of them, the exponential, spherical, and Gaussian. All right. So if we're going to look at our semivariance for each of those 3 models, we have our exponential, our spherical, and the Gaussian. On these, the nugget is 0 for each of them. The sill is going to be 1, and the range changes by the actual model itself. Okay. So we have C as our partial sill, H is our distance. So this would be a Euclidean distance between 2 points. A is our range, and we have our nugget. So these 3 models here are what you typically use in the spatial concept when you're looking at simply that. So we have that broken out, and notice that the nugget is always out separate just in case it's 0. You can't have a 0 nugget model, nothing wrong with that. All right, so let's expand this to our spatial temporal set. We're going to look at 3 particular models, which are combinations of the models from the previous slide. So we're going to have something called the separable model. And what you're doing there, you're taking your spatial variogram and multiplying it by the temporal. Is that easy? Yes, it's the easiest one. You can break everything out. However, it's not particularly real life conducive, if you will. Again, with a lot of theoretical things, the easiest is not always the best when you're fitting real data sets. We have something called a product sum model. And finally, the sum metric model, which is my particular favorite. you have both the spatial and the temporal, and then you have a combination using your distance and your time, also something called kappa, which is an anisotropy parameter. And again, we'll talk about that in a little bit. So let's talk about the empirical background. We've got our theory. We're going to fit sample space-time variograms, and we're going to use those against our authorized model to find the best model. And as promised, we fit our separable, our product sum, and sum metric models. So for our new model using our MPI Fort, we're going to keep the sum metric model because it is really the most appropriate for the real world. For our other two setups, using the Windows and the Mac, we'll still fit all three of the models, and we'll select the best of the three. So actually all of the methods are going to fit all three models. So we're going to obtain the estimates for our SIL, our nugget, range, and anisotropy. I can calculate our mean, covariance matrix, and the predicted values based on those. All right. So up to this point, we're using the R techniques to get our initial semivariograms. Now, at this point, the other methods are going to use something called Kriging and process that way. And here with our new method, we're going to actually break this out into matrices. So ordinary Kriging, you have to get an estimate of your mu hat. So you do this in the following manner. And we're going to use our covariance matrix for the sum metric model. So essentially it's the same kind of thing that you saw in the semivariance. For a 1-point forecast, we use our final equation here, and we use our mu hat in that, and the inverse of our covariance matrix. So this is a 1-point forecast. It's very easy to generalize this in space and time. So let's look at our big project. We're going to look at the Irish wind data, which is pretty much standard fare in geostatistics. It is discussed very thoroughly in PBESMA in 2004. The original data set appeared in Hazlitt and Raftery in 1989. So we have daily wind speeds at 12 stations around Ireland. The original data set runs from January of 1961 through December of 1978. So we're going to look at this first in a 3-month interval, 1 year, and then in 1-year increments until December of 1969. And our goal is to produce our spatial temporal grid with essentially interpolations. Okay. So as promised, I ran the existing process on our 2-core MacBook Air, the 6-core Windows laptop that really was not using the multi-core. So our new process from our MPI Fort, we use our 6-core Windows laptop, and R has been compiled with the OpenBLAS package. That's the basic linear algebra subprograms rather. I've rerun the study within the last 2 weeks to reflect the R version 4.0.0. I have not used it on 4.0.1 just to make sure we had everything in line for the talk. So as I mentioned, your output is going to be a spatial temporal grid with interpolated values. So you will have these at particular longitude and latitude at particular times, and then your interpolated value. All right, so let's take a look at our results. So when we did our 3-month study, so that was from December of 61 through March of 61, the Mac took about just short of half a minute. The Windows is 0.29 of a minute, and our new method is the 0.28. So that's pretty good. Then when we go to 1 year, so that's your January of 61 through the end of 61, things start ticking up very quickly with the Mac and the existing method on the Windows. Our new method is still showing very nicely. It's only 2/3 of a minute. Then as we go to 2 years, the Mac goes over an hour, and it cannot handle anything more than 2 years. When we look at the existing process for the Windows, that's running at 27 minutes, it will go to the 3 years. It will take 113 minutes, just short of 114, I should say. And again, it cannot handle the remaining years. So we continue with our new process. We have very, very nice results as we go up. And our last one we were able to get runs from January of 61 through December of 1969. So even that still only took 35 minutes. So the table is nice. The graph actually is even more stark. So you can see how the times shoot up for the existing method and then they just drop. And our new method continues on and it has the very reasonable time. Okay, so I also looked at some temperature data from Cuba. In this one, I looked at 4 locations, daily data from 2015 through the end of 2016. I ran our new procedure, and you're going to see we're going to take our interpolated values and actually produce a map. So we'll see that in a second. The process only took 1.37 minutes. And there was a notable measure of anisotropy going from east to west. So the way to think about that, if you think about you're looking at a field and maybe it has some kind of a furrow that runs from east to west, that's the sort of thing where you're going to pick up anisotropy. When we were looking at the Irish data set, you set the default kappa of 10, and it stayed almost consistently 10 throughout the entire study. In this one, we started at 10 and it shot up to 154. Again, that makes sense when you think about you're on an island, you are going to have temperature changes based on an east to west trajectory. So let's take a look at the output. So when we have this, we're going to have longitude, latitude, and time. So we're going to have a dynamic Google Earth map. We run back to the beginning. We click the slider. You see how things change over time. When you get to the end, I'm just going to get.
Sorry, to disturb you.
Sure.
Were you trying to show the map just right now?
Yes. It's not showing. Hang on.
You are just looking at the slides.
Right. Okay. So let me go back here. Thank you for the update on that. All right. Why is this not letting me go back into Zoom? No, that's not it. Why isn't it? So let me try one more thing. Okay, so.
Yeah, what if you unshare?
Okay, stop sharing on that one and go to the other one. Brilliant, thank you. Okay, now let's try this. Okay, so.
Yeah, all
as
good.
Promised. All right, so here we have our map. We're going to start back to the beginning of 2015. You click on the slider. You see how things change over time. Now I'm just going to go to Havana, pick one of the pins at random, and you get your data. So you get your temperature estimate. And this would be at the end of 2016. So you have a temperature of 71 degrees at that particular longitude and latitude. So it's a lot of fun to have the time slider on that. Okay, so let's go back to our other thing. All right. So again, you're going to see your anisotropy as your time and your longitude changes. Okay. So now here's the fun stuff. Let's talk about how this actually works. So I get a lot of questions. Why do you use Fortran? Why don't you use C or C++? And this is a carryover from working on the supercomputer. I started out using C and the existing RMPI package. I assumed that was just going to run great. But I didn't get very good speed up. And I was talking to one of my colleagues and he says, well, you know Fortran, why don't you give that a shot and see what happens? So the RMPI package actually has R functions that are calling the MPI subroutines. So MPI is not a language, it's simply a set of subroutines that will work with C and Fortran. So I experimented with all this, and then I started to get these great speed ups. So I was pretty excited about it. All right, what do you need? So with what we're doing, you have to have an NVIDIA graphics card, but for many of you, if you have any kind of a laptop that does gaming, I'm willing to bet that you're going to have an NVIDIA card. There will be a sticker actually physically on your computer, and you'll see that you have it. The key to this is going to be your PGI Community Edition compiler. So you're going to get your PG Fortran and your PG F90. You also have to download the latest version of your CUDA drivers, and those come from the NVIDIA website. And you'll see why we need those in a minute. So our other tool that we're going to use other than OpenACC is going to be MPI. So you need the Microsoft MPI for that. And you also need Visual Studio. Again, that's going to support your PGI compiler. You don't have to use Visual Studio. It actually ties in for you. Again, I'm not necessarily the biggest fan of Visual Studio, but that's because I'm not all that strong in C or C++, so for what it's worth. All right, so I developed an R package for this process. And the nice thing about it, everything we do is done with free software, so we don't have to worry about buying things. So we're going to start with Avraham Adler's website on building OpenBLAS. So that's going to be for Windows. For those of you that use Linux, or I believe on some of the Macs, not all the Macs, that will come built in. So then you're going to compile R with that OpenBLAS. Again, you're going to be compiling from source on Windows. So if you've ever done that by source and you've looked at something called the Makefiles rules, you will see something like use Atlas and you give it a path. That ties you in to your OpenBLAS. All right. So when you build your R package, when you have foreign programs in your source directory, usually you have a file called the makevars. And when you do your build and your check, that will take care of building your language. But when you use your PGI compiler, that makevars file doesn't work anymore. So what you're going to do is get into something in the etc. x64 and look at a file that's makeconv. So if you go in there and take a look at it, it has your compiler codes and your flags that you will use. So what you're going to do is actually go into that file and set it up that it reflects the PGI compiler and the flags that go to that. So once you run that, you're going to do your build and your check, and you'll be able to build your package. Now, the thing you have to remember is put the makeconv back. You don't want that when you're downloading packages in the future. That's just good when you're actually building your package. However, if you're just going to have a single program or a couple of programs using OpenACC or MPI, you just use your PGI compiler from the command line. You don't have to go through changing out your files. All right. So how does OpenACC work? So again, we're using Fortran, and we use something called directives. So the OpenACC is going to move data from your host, your regular CPUs, onto the GPU device for quick processing. So again, that ties into your graphics card. And this is what it looks like. So you've got your CPU with your multiple cores. Even if you have as little as 5% of code, you're going to get very nice speed up when you push your data onto the GPU. So for instance, on the computer that I use, I've got 6 cores in my CPU, but on the GPU, I have 768. So you're going to pick up a lot of speed in relatively short amount of time. Okay. So when you're working with OpenACC, do you have to have a lot of programming? Is there a lot of extra stuff? The answer is no. So if we just look at our do loops, this is essentially calculating your Euclidean distance. You actually just need 2 commands or 2 directives to make this run. So you're going to have your ACC loop sequence, and you're going to end the loop. Also notice that the leading character on these is going to be your exclamation point. So you could actually take your program and leave it as is, because if you try to compile it on another compiler, it will work because it's going to see that exclamation point as a comment. So you don't have to worry about changing anything out. All right, so let's take a look at an example. So nothing like a little bit of code for fun. So we're going to have our subroutine, and this is going to tie into R. We're going to pass your vector size, a vector, and we're going to calculate the time. Now, something that's a little bit interesting when you're using the OpenACC, you need the statement that has the exclamation deck $signs and so on. That will actually bring it in to R. So here we have our program. It's very straightforward. Notice that we have that statement use CUDA for. That's going to tie in to our CUDA. Remember, we downloaded that, and that's what helps bring your data from your host, your CPUs, out to the GPU. So this is, just regular, straightforward, nothing particularly interesting. We're just going to take our counter and add 2. All right. And the nice thing about this is you can run this directly in R. I have a DLL, so you need your dynamic library in R when you're using it on Windows. I just put together my n of 1024 squared, put together a numeric vector of all zeros, and you just call your Fortran subroutine, your AC1, you run it, and the time for this was 0.002 seconds, so not too bad. All right, so let's get back to our geostat. We're going to take our SIL and our nugget, and we're going to start building our matrices and combine them. So we're going to use our OpenACC to actually produce the matrices. So as we saw a couple of slides ago when we did the distance, that's part of it. That's a small part of that. And we're going to return the matrices as a very long extended vector, and we're going to rebuild it once we get back into R. So the next step is to use MPI, and we're going to use another package called PBD-DMAT. That's going to use our MPI. That was put together by Drew Schmidt, Wei Sum Chan, and George, and I believe his last name is Osterhoff. Sorry if I mispronounce it. And this is going to use our MPI. We're going to split our matrices into submatrices based on the process rank. And that package creates special structures for large matrices. So if you just try to use the matrix without this, it's just not going to run. But we're going to split it out, and that's going to help. Okay. So how does our MPI run, or work rather? So we initialize the process. We look for the world or the universe, the number of processes. We're gonna check the rank of the process, and that's going to run from 0 to n-1. You're going to have calculations, again, depending on what you're doing, and we have a finalization call. So those interim four steps, initialize, checking for world, checking rank, and finalization always take place. The calculations will be context-based. All right. So here's just a very simple program. When I do my initialization, I'm just calling a subroutine MPI init in Fortran. You're just going to compile that. Very simple. Then you're going to have a function that will actually call within R. You're going to initialize just calling your finit function. All right. So let's look at a nice MPI example. And one of the typical examples that you see in MPI, you're going to do an integral. So we're going to bring in our RMPI fort. And I also did something called sum.dll. I'm just going to integrate from 0 to 1, x to the 5th. I know, could it be any more simple than that? So here we have our init. Here's the number of our universe. Here's our number for our rank. And we're going to set up the code that's going to actually calculate your integral based on the trapezoid method. And then finally, the last thing, you're going to call the sum program. And it's going to give the sum of all the integrals. And here, of course, we have that finalize. Here's again, a very, very simple Fortran program, which is the sum. And you use a very nice function called MPI reduce. So it's going to take the pieces that you bring in from the integral. We want the sum in this case, and it's going to do the addition. And let me just go back. The rank one is kind of like the boss, and the other one's the worker. So you're going to, when you have a rank of 0, that's when you're going to get your total results. All right, so that's very nice. Also with MPI reduce, you can get a minimum, a maximum, a minimum location. So that's very useful. All right. Now, when you actually run this, you're going to have to run from the command line. You're going to use MPI exec. You're going to put in the number of processes. And then in what I'm doing, I'm using an R script and writing it out to a file. So we were integrating from 0 to 1 of x to the 5th, and we came up with our 0.1666. So we are relieved. A quick note, when you're doing a lot of your MPI, even though if you have more than 4 cores, you typically want to use the number of processes that's some kind of a power of 2. It usually works out better because, let me scroll back a second. Typically when you do your stuff, you're going to have, say, a number of steps that is also going to be a power of 2, and it will make division within the processes much simpler. All right. So again, going back to our real stuff, our job is to invert that final covariance matrix. Here again, we're going to use that PBD DMAT package. So in this final segment of our Irish wind data, we're inverting a 39,000 plus by 39,000 plus matrix on the laptop. We get that done in our 35 minutes. So that's not too shabby. All right. So some of you, if you're used to or have had occasion to use CUDA Fortran, does it work with R? Yes. However, this is a big however, you start talking about number of threads, number of blocks, it gets very complicated very quickly. The OpenACC is doing the same sorts of things that you would be doing in CUDA Fortran. It's much easier to work with. As you saw, we only needed the 2 functions and we just let it run. So again, that's one of those things, if you're used to working with it, yes, it will tie in with R. You can create your dynamic link library and it will work. All right. So our conclusion, our speed up was unexpectedly good, better than I thought it was going to be. Also, the data size was better than I thought it was going to be. When I saw on the existing methods, when we were coming up with 2 years and 3 years, I had no idea we'd be able to get out to 9 years. And of course, I want to try this on a laptop with more core and more memory. Okay, what kind of questions do you have, please?
Thanks, Erin. That was an excellent talk. If you are able to stop sharing the screen and start your video, we could start a Q&A session.
Great.
Wow. So that was a lot. There was a command line that actually called MPI, where we had an R that called stuff also supported by Fortran. So there is, I would say this was a very advanced talk. We have a couple questions from the chat. Let me start with the logistics one. Is there a chance that you can share some slides or the full presentation so that we could actually put it down under the video in the description?
Absolutely, positively, and I'm happy to share any of the code. I can put the RMPI, the latest version, up on GitHub, and I can send you the link to that. Also, some of those little programs, I'm happy to send those out. Just shoot me your email. We'll get it out to you in no time.
Okay. That would be great. So yeah, let's get the code on GitHub, and then we will post it under the video so people can reach and have a look. And also they will have a way to contact you, since your email is provided on your GitHub account.
Yes.
On your profile. That's great. Okay, so let's dive into some details. So just to let you know, we had people from 5 continents. That was a pleasure to see people from Senegal, Philippines, Romania, United States, Costa Rica, Ireland, Poland, Texas, that states. Yeah, and the first question is from Ahmadu. This is very technical. I am not sure if I would make it a proper question, but you might, as an expert, understand more from this one. Have you tried Intel MKL instead of OpenBLAS? And if you could tell what's the difference, and yeah, have you tried it, and what's the comparison?
No, I haven't. I understand that it's it would be comparable or even slightly better, I would guess. But yeah, that would be a very interesting thing to try. Absolutely. Now, one thing, when you're doing the OpenBLAS compilation, you're going to end up with a file that's going to go along with the processor that you have. So for instance, you may have heard of Sandy Bridge. So that's one of them, Nehalem. Now, the one that I have in my particular laptop is something called Haswell. So it's really, when you're doing that, a lot of it's going to be the function of the kind of processor. I'm guessing the Sandy Bridge would be incredibly fast. I've read a little bit about that. I think that would be your best bet.
Okay. There's another one from Ahmadu. Does OpenACC PGI works with RCPP?
Work with, excuse me, what was the last part?
RCPP.
I honestly don't know. I do know that it works with plain G-Fortran, or I should say the latest versions of plain G-Fortran. OpenACC needs the NVIDIA compiler, or excuse me, the graphics card. However, you can use on the ARM architecture, I believe you can use kind of a subset of OpenACC using the regular G-Fortran, but I'll check on that and get back to you. If you just send me your question, I'd be happy to check that out. Thank you.
Yeah, so folks, we will upload the GitHub URL under the description of the video after the stream is done, and then there will be Erin's GitHub profile that has the email that you can use to contact her. Okay, so this is another question that I also had in my mind. So we saw a bit of Fortran. How easy is to learn Fortran when you are an R programmer? How much do we need to know about Fortran to actually use this flow that you presented? And do you have any good resources for beginners that you might recommend?
Sure. So usually the best way to do the Fortran when you're going into a new language, take somebody else's code and modify it, see what you need to do. A lot of this stuff is very, very straightforward. Of course, I was going to say it's a lot easier to say that once you've been doing it for a while. But I mean, there's not tons of really complicated stuff. One of the best resources is the Introduction to Fortran Programming by Ian Chivers, and I can't remember the second author. That's actually in the 4th edition. And I believe that you can get the 3rd edition online in a PDF. So that's also a good place to start. There are lots of resources in that. They have lots of examples that you can download and compile.
Can you envision if there will be a time point in the future where we will not use Fortran anymore for this kind of computations?
Yes, yes. The thing that is a little bit concerning to me is the speed. Fortran is going away. There's still a few people at NASA that use it. It's losing a lot of popularity. The only, again, as I see, the trade-off is going to be with speed. So the MPI will work with regular C. I read fairly recently that a C++ no longer works with MPI. It did for some time, but I don't believe that it still does. So that's something to keep in mind.
Okay, got it. So there are always kind of trade-offs. The
Sure.
accessibility and actual speed of the program makes sense.
Right.
I was.
I'm sorry. Go ahead. Sorry.
Go ahead. Go ahead.
The Portland group always is going to contain the Fortran, or at least for the foreseeable future, because of using that in also in conjunction with the CUDA Fortran. So they do want to keep that going as long as possible. Sorry for interrupting.
Yeah, no, good to know. Good to know. I was curious if you can extend this setup, this workflow to more than one machine.
Yes, absolutely. I haven't done it for a while, but particularly with the MPI, it's very easy to extend onto a cluster. And yeah, that works really, really well. And there's an old reference. It's Peter Pacheco, Parallel Programming with MPI. The examples in there are actually in C, so that will make you happy. But he also describes setting up a cluster in there.
Okay. Okay. Yeah, this is very advanced talk. This is a rare occasion where we have this kind of a content. So I'm really happy to have you tonight, today. And also I saw in your program, you were returning a vector instead of matrix. Is it because of some kind of a performance issue, or is it a Fortran feature? What is the motivation for actual this way of returning your results?
So when you're calling Fortran from R, it won't take matrices. So that's why you need to flatten them out and bring the results back in that way. Okay. So even when I was using when you use the PDB DMAT, you're going to bring stuff in as a vector and then convert it back. So most of the vectors, or excuse me, the matrices are going to be symmetric. So it's pretty easy just to put them back in their shape. But yeah, anytime you call Fortran from R, you have to return vectors.
Okay, so that's a feature of the language. Makes sense. Yes. Makes sense. I also noticed that you verified the structure on R4.0. That's pretty amazing that it works for the current R release. Are there any suggestions or procedures that you have or you do to maintain the reproducibility? I see there is a lot of external dependencies playing at the same time next to R. Do you recommend any reproducibility procedures?
So one of the things that you have to do, check with the PGI compiler and the CUDA drivers that you're downloading. For instance, I have CUDA drivers 10.2, but the community edition of the PGI compiler only works with 10.1. So you do have to keep that in mind. Make sure, I mean, even if you try to compile with the 10.2, it'll spit it out. So just kind of watch to see what the parts contain. And even until fairly recently, the PGI compiler only used Visual Studio 2017. It's just recently switched to the 2019. So again, just read through the documentation for that. That's usually the biggest problem. One other quick thing, if you happen to be working with the R development, if you bring that down, sometimes the PDB packages don't work with that. You really need to have the regular version. So that's just something to be aware of.
Yeah, totally. There is a lot of cooks in this kitchen. So there's a lot that you need to have in your mind. Erin, that was very advanced. I am really happy that we had you here. And this is already all of the questions. I have a feeling that this needs to marinate in our heads, and probably audience will need to have a chance to digest, dive deep into this video, have it one more time or at least twice, look at the codes on their own, and probably then more questions will arise. It was a pleasure to have you here tonight, and I'm very thankful for having you.
Well, thank you. I really enjoyed this and hope you all got something out of it.
Yeah, I took a lot, and I hope that other people do as well. Folks, so we are not having a webinar next week since there is an European R users meeting happening online. You can check their websites to see details where they will stream. If you also go to our channel on YouTube, we have recommended channels on the right where their channel is, so you will have a quick way to find their channels with the stream that will happen next week. From the other hand, we just started the registration for YR 2020 conference that will also happen remotely. It will happen in September between 24th and 27th. If you go to our channel, we already put placeholder for the streams for the first and the second day of lectures. So if you click set a reminder there, you will be notified that we started streaming. And also you can go to our website, yr.pl/2020 to get registered. Thanks for your time tonight, Erin. Once again, it was a pleasure. The talk was really advanced. Thank you for that. And yeah, guys, see you in the next 2 weeks.